Okay. Hello. We will start slowly uh, because we have only 1 hour to discuss. So in the last class, we have been discussing about relations, and in that we talked about two properties of relation, which are reflexive and symmetric. Now today, I will just quickly go through transitive relation, and there is one important point that I have to make in transitive relation, which we will see today. And after that, I suggest everybody to have pen and paper with you. We will solve some 5 problems today, which aligns to your graded assignment questions. So yeah, we will do that also. Okay. I hope this screen is visible. Yes. Okay. So what exactly is transitive relation? A relation. This particular relation should be defined from set S, one set, onto itself only. Okay. And this should be a binary relation first of all. And this binary relation R is said to be transitive. Again, IFF means if and only if. So if and only if for every pair of elements, so you need to have two pairs like x comma y and y comma z, which are there in your relation R. Then check for the third element, which is xz. So the first element in the first pair and the second element in the second pair, they form a pair, and that x comma z should be in your R. So if this is satisfied by every pair x comma y, y comma z, then the relation R is said to be a transitive relation. So I repeat, in order to check for transitivity, you need 3 elements basically. Okay. So you have to take 2 elements which are of the form x comma y and y comma z. So the element which ends with y and the other element should start with y. So x comma y, y comma z. If there are elements like this, so if you find a pair like this, then check for the third element which is of the form x comma z. Okay. If that is there, then your relation is transitive. If that is not there, your relation is not transitive. If it fails for one pair, then it will not be transitive. What does that mean? If you find x comma y and y comma z, but you are unable to find x comma z, then it will not be transitive. Okay. So for example, here you see set S which contains 1, 2, 3, and I define a relation R which is like this. It contains 1 comma 2, 2 comma 3, 1 comma 3. Now if you see, if you stare at the 3 pairs we have in R, the first pair is 1 comma 2 and the second element is 2 comma 3. So now you can see this is of the form x comma y and y comma z, where see 1 comma 2 and if there is 1 comma 2, you have x comma y. Then search for, are there any elements which starts with 2. So if you search, there is one element which is 2 comma 3. So now 1 comma 2, 2 comma 3 forms a pair like this x comma y and y comma z. Now our job is to search for x comma z, which is 1 comma 3. So just check for whether 1 comma 3 is present in that or not. And again, if you see 1 comma 3 is present, therefore 1 comma 2, 2 comma 3, there is 1 comma 3. And with respect to 1 comma 2, this particular relation is transitive. Okay. Now go for the second element 2 comma 3. Now think of it like x comma y. Then see whether there is any element that starts with 3. If you check, there are no elements. So what we conclude is, with respect to 2 comma 3, if you treat it as x comma y, you don't have any y comma z to check for x comma z. Okay. So what I mean is 2 comma 3, if you treat it as x comma y, now x is 2 and y is 3. Now you need one more pair like this to check for x comma z. So if you need one more pair, that particular element should start with 3. And in this particular relation R, you don't have any element that starts with 3. Therefore, you don't even have to check for x comma z pair. Okay. So if you have x comma y and y comma z, then check for x comma z. So this is the important point I wanted to mention. If you only have x comma y, you will not check further. If you have x comma y and you don't have y comma z, you don't check for x comma z. Okay. And we conclude with respect to 2 comma 3 or x comma y, that is transitive. Okay. So you started from 1 comma 2, which you thought as x comma y. Then you went for checking, is there any element that starts with 2, and you found out that there is 2 comma 3. So therefore 1 comma 2 and 2 comma 3 forms a pair like this. Only then you check for x comma z, which is 1 comma 3 in this case, and that is also present. So therefore, with respect to 1 comma 2, this particular relation is transitive. Then when you move to 2 comma 3, for 2 comma 3, you need to have some other element which starts with 3 to check for transitivity. But there are no elements which starts with 3. Therefore, with respect to 2 comma 3 also, this is transitive. Then you move again, move to the next element. You pick 1 comma 3 as your x comma y. Now, if 1 comma 3 is x comma y, then again 3 is y. So you need some element which starts with 3, which you don't have. Therefore, you won't even check. You conclude this is also transitive with respect to 1 comma 3. So it is transitive with respect to 1 comma 2, transitive with respect to 2 comma 3, transitive with respect to 1 comma 3. So it is transitive with respect to all the elements that are present in R. Therefore, the relation is transitive relation. Any doubt in this? Whatever I discussed. Okay. So let's see a couple of problems. So now you see another relation R1 I defined on the same set S. So you have 1 comma 2, 1 comma 3, 2 comma 3, 3 comma 2, 2 comma 2, 3 comma 3. So quickly, can you all tell me whether this particular relation is transitive or not? You can also answer via chat.
Is transitive.
Okay. So you just have to start from one element, take 1 comma 2. Now treat it as x comma y. That means x is 1 and y is 2. Now search for another element which starts with 2. There are two such elements, 2 comma 3 and 2 comma 2. Right? Now you have multiple pairs. For 1 comma 2, if you treat it as x comma y, then there are 2 comma 3 and 2 comma 2 which starts with 2, which can form y comma z's. So you have to check for each y comma z again. So if you start 1 comma 2, then there is 2 comma 3 and 2 comma 2 which can be your possible yz, y comma z pair. For 1 comma 2 and 2 comma 3, you need to have 1 comma 3, which is xz. For 1 comma 2 and 2 comma 2, you need to have 1 comma 2, which is already there. Okay. So if you choose 1 comma 2 as xy, now in the first case, you choose x as 1, y as 2 and z as 3. If you choose like this, then you need to have 1 comma 3 in your relation. Search for 1 comma 3, whether 1 comma 3 is there or not. And if you see 1 comma 3 is present, so that is all right. Transitive relation is satisfied there. Next case, what happens is that 1 comma 3 is there. Next case, what happens is you choose 1 comma 2 and 2 comma 2 as your x, y and y, z. Now, if you choose like this, your x, y, z's will be 1, 2 and 2. Okay. If this is the case, you need to have x comma z, which is 1 comma 2. That 1 comma 2 is already present. Okay. Similarly, you check for all other next element. You move to 1 comma 3. You move to 1 comma 3 and treat it as xy. Then you will see that you have to get other elements which starts with 3, but you will have 3 comma 2 and 3 comma 3, which forms pairs. And 1 comma 3 and 3 comma 2 you choose. Then you need to have 1 comma 2, which is there. 1 comma 3, 3 comma 3 if you choose, you need to have 1 comma 3, which is also there. So with respect to 1 comma 3 also, this is transitive. Then move to 2 comma 3. If you move to 2 comma 3, 2 comma 3 is your xy. Then you look for elements which starts with 3, 3 comma 2 and 3 comma 3. If you choose xy as 2 comma 3 and yz as 3 comma 2, you need to have xz, which is 2 comma 2, which is there. Similarly, if you check for all elements, it will be there. So all elements satisfies the transitive property. Therefore, the whole relation is transitive. Now, next comes another relation R2, which is all the pairs AB such that A is a factor of B. So, what is the factor? Is 2 a factor of 4 or 4 a factor of 2? Anybody?
2 is a factor of 4.
Correct. So, what are factors basically which divides the number? So, all the numbers that divides some big number are factors of that big number. Okay. Now, can you all tell me whether this particular relation given here is a transitive relation or not? Okay, I'll give you a hint. Just take it is not transitive. Okay. So take all, just explicitly write down what all A comma B's that can be in R2. What are the possible A comma B's? Can 1 comma 2 be an element in R2?
Yes, sir.
Yes, correct. Can 3 comma 9 be an element in R2? Yes. 9 comma 3?
No, sir.
No. Okay. Now, can 2 comma 4 be an element?
Yes, sir.
Yes. Can 4 comma 8 be an element?
Yes, sir.
If 2 comma 4 and 4 comma 8 is an element, will 2 comma 8 be in your element, in your R2?
Yes, sir.
Yes, sir.
If there is a pair A comma B, let's say, or X comma Y is in R2, what does it mean? X is a factor of Y. Some xy. If you treat some xy, what does it imply? X is a factor of y, only then x comma y will be in your R2. Now you pick some yz. If yz is in R2, what does it imply? Y is a factor of z. Correct? Now if x is a factor of y is a factor of z, will it imply me that x is a factor of z?
Yes, sir.
Right? So what does it imply? X comma z will also be in R2. If x comma y and y comma z is in R2, R as the relation, will it imply me that x comma z will also be in R in
Yes,
the
sir.
relation?
It should
Yes.
imply.
It should imply. If it implies, will this be a transitive relation?
Yes, sir. It will be.
Yes. So you can, that is why I said, if you don't have, or if you are not able to understand it mathematically, write it explicitly. Just write down what are the elements that are present in R2, 2 comma 4, 4 comma 8. Create these pairs, x comma y comma z pairs, and see whether x comma z pairs will be there in R2 or not. So 2 comma 4, 4 comma 8. It will also have 2 comma 8 because 2 is a factor of 8. Similarly, 3 comma 9 and 9 comma 90. So these two will be in R2. Not only these two, if this forms x comma y comma z, 3 comma 90 will also be in R2 because 3 is a factor of 90. So this is how the proof goes. So if you have any p comma q and q comma r in R2, this implies that p divides q, and if q comma r is in R2, q divides r, which will totally imply p divides r. So if that, what does it imply? If p divides r, p is a factor of r, therefore p comma r will also be in R2. So for every pair p comma q, q comma r, you will have p comma r. So yeah, the last thing which I wanted to mention is this: if you have only one element, okay, in your relation you have only x comma y, can this relation be called as a transitive relation? So I think most of you will have a lot of confusion on what if we have only one element in R.
Sir, it should be no, sir. If
Yes,
it take y
it
and
should
z,
be okay. It should be no, or it should be transitive.
it should be transitive, sir.
It should be transitive. Okay. So are there anyone who feel like R3 shouldn't be transitive? No one? Oh, great. Great then. So R3, so you have x comma y, but you don't have any yz to check for xz. So you don't, there is no checking at all. So if you have only one element, you can freely, confidently say that this is transitive. Okay. So since R3 contains only one element, there is no other element, we will conclude that R3 is transitive. Okay. So the checking will come only when you have two elements x comma y and y comma z. Only then you go check for x comma z. If you have only x comma y, blindly you can say that particular relation R3 is transitive. Yes.
So, what if the relation only has two elements and not three? Then, how can we compare and say that it's transitive?
Then again, see, those two elements should be, if it is of the form x comma y and y comma z, something like 1 comma 2 and 2 comma 3, or 1 comma 3 and 3 comma 4. So if you have these kind of elements, then definitely you need to have the third element. But if you have elements like 1 comma 2 and 1 comma 3, for example, then with respect to 1 comma 2, you don't have any y comma z or any element which starts with 2. We conclude that with respect to 1 comma 2, that is transitive, and move on to 1 comma 3. Even when you move on to 1 comma 3, you have 1 comma 3, but you don't have any other element that starts with 3 to check for xz. Even
Yes, sir.
then you conclude with respect to 1 comma 3, this is transitive. So with respect to 1 comma 2 transitive, 1 comma 3 also transitive, therefore the whole relation will be transitive.
Okay, sir. Thank you, sir.
Yeah. Okay. So I think we have a couple of more examples also. So this particular example, we saw it last class. Again, we have it again here. So we have defined a relation R. It contains all the pairs xy where x plus y is odd. So will this relation be a transitive relation? So remember, always for transitive relation, you randomly take some xy, some yz, and see whether xz will be there in R4 or not. If you find any contradiction, then this will not be transitive. If you are unable to find contradiction, then it has 99.99% chance that this is transitive. Yes,
Sir, it is not transitive.
it is not transitive. Okay. Any other answers? So let's see. So we have A is a set of natural numbers that starts from 0 to infinite, 0, 1, 2, 3, 4, and so on. You just write down what all elements that R4 can contain. This is a random pick. So 0, comma 1, 1, comma 4, 9, comma 6, 6, comma 5, and so on. Now just pick so 0, comma 4, 9, comma 5. Yeah. Okay. So now you have 0, comma 1 and 1, comma 4, which forms x comma y and y comma z pair. Right? Now, if it forms x comma y and y comma z pair, then definitely, in order to be transitive, your 0 comma 4 should also be in R4. And similarly, 9 comma 6 and 6 comma 5 forms xy yz pair. For this particular pair, you need to have xz, which is 9 comma 5. Okay. So 9 comma 5 should also be in R4. Now, is it always the case that just like we proved in the previous example, can we say m comma n comma p belongs to R4, which implies m plus n is odd and n plus p is odd, which may imply m plus p is also odd.
No,
Right?
sir.
No, right? Because you see 0 comma 4 or 9 comma 5 will not belong to R4, because if you add 0 to 4, it is even, which will not be in R4. And one example is sufficient to break the property, transitive property. We straight away conclude this is also false. We straight away conclude that R4 is not transitive. So for proving not transitive, you just require one example where you have the pairs x comma y, y comma z, but you are not having x comma z in your relation R4. Okay. Not only for transitive, you can use it for symmetric, reflexive, all the properties. You can contradict or you can say they are not by just coming up with one example. But for proving, you need to prove for all the elements, all pairs. For transitive, for every pair x comma y comma z, you need to have x comma z. Only then you can say that is transitive. Okay. So yeah, think that's all about transitive. Yeah. Finally, equivalence relation, as you all know. So if R satisfies all three, then R is equivalence relation. So this particular identity relation, which we discussed in the last session, this identity relation satisfies all three properties. Therefore, this relation is an equivalence relation. And also, if you have any relation like this, A comma B, A comma B are from people in India, and R1 contains all the pairs A comma B where A and B lives in the same city. Even here also, you can check for reflexivity. Reflexivity is very simple. If you are living in India and in one city, then you will live in that particular city. It's reflexive, right? So x comma x will always be there for every x. For symmetricness, if x comma y is in R1, that implies x and y live in the same city, which more or less same as saying y and x live in the same city. So y comma x will also be in R1. Therefore, this is symmetric. Similarly, if you have any pair like x comma y and y comma z, that in R1, that implies that x and y live in the same city, y and z live in the same city, which obviously implies that x and z will also live in the same city, which implies x comma z will also be in R1. So for every pair x comma y, y comma z, you will have x comma z also will be in R1. Therefore, this is reflexive, symmetric, transitive. R1 is the equivalence relation. Okay. So I had a small exercise. So you can map all the left side. You see, this is a table. So you have two columns in the table. The left side is the relation defined on the set yes, where S contains 1, 2, 3 elements, and there are 4 relations. And on the right side, in the second column, you see the properties of the relation. Now, what you have to do is you have to just map. So it's like matching. So you just have to match R1 to all the relations that it satisfies. So all the properties that it has. Similarly for R2, R3, R4. Okay. So what about R1?
R1 is symmetric, sir.
Okay, R1 is symmetric. Is R1 reflexive?
No, sir.
No. Is R1 symmetric? So for symmetric, for every x comma y, we need to have y comma x. So for 1 comma 3, we need to have 3 comma 1, which is there. And 3 comma 2, we have 2 comma 3, 1 comma 1, we have 1 comma 1, 2 comma 3, 3 comma 2, 3 comma 1, 1 comma 3. So therefore, R1 is symmetric. Okay. Is R1 transitive?
No, sir.
No. So when we are saying no, we just need one example to contradict, right? So what is that one example we can see?
We have 3 comma 2 and 2 comma 3, but we don't have 3 comma 3.
Correct. Good.
Sir,
Hmm.
can't we say there is 1 comma 3, 3 comma 1, and there is 1 comma 1?
See, that is what I said. For every pair, in order to say that is transitive, you need to check for every pair x comma y, y comma z, you need to have x comma z. So you just showed me one pair, which is x comma y, y comma z, x comma z. That will not be sufficient to say that is transitive. For transitive, you need to show me for every pair like that. So just now, Magesh, I guess, Magesh has given us 3 comma 2, 2 comma 3. So this forms x comma y, y comma z pair, but there is no 3 comma 3 in R1. So for this particular pair, there is no xz, which breaks the transitive property. For proving something, you need to prove for every possible pairs, for every. So every is different from one, right? It is not sufficient to just show one x comma y, y comma z, x comma z tuple. If you have x comma y, y comma z, then definitely there should be x comma z for every possible pair. For every, I mean, I can give you one more example. 1 comma 3, 3 comma 2. You see the first two elements itself. So that forms x comma y, y comma z pair. But you don't have 1 comma 2. Correct? So if you fail for one particular case, then the whole relation will not be transitive. For telling transitive or for concluding it as a transitive relation, you need to check for all possible pairs, for all possible pairs. Okay?
Yes, got it.
Okay, so R1 is not transitive, therefore R1 will not be equivalence also. So what about R2? Is R2 reflexive?
R2 is not reflexive, sir. We don't. Oh, no, it is reflexive, sir. We have 1 comma 1, 2 comma 2, and 3 comma 3.
Correct. So R2 is reflexive. Is R2 symmetric?
Yes, sir.
Yes. So for symmetric, again, 1 comma 1, you need to have 1 comma 1. 2 comma 3, you need to have 3 comma 2. 3 comma 2, you have 2 comma 3. 2 comma 2, you have 2 comma 2. 3 comma 3, you have 3 comma 3. For every element, there is symmetric element. Therefore, R2 is symmetric. Is R2 transitive?
Yes, sir.
Yes. R2 will also be transitive. Again, you start with 1 comma 1. So you have 1 comma 1, which is x comma y. Search for another element which starts from 1. Except 1 comma 1, there is no element that starts with 1. Therefore, with respect to 1 comma 1, it is transitive. Take 2 comma 3. So 2 comma 3 now acts as x comma y. See for other elements which starts with 3. There are two such elements, 3 comma 2, 3 comma 3. So now 2 comma 3, 3 comma 2 forms xy yz pair. With respect to this pair, we need to have 2 comma 2, which is there. Again 2 comma 3, 3 comma 3 will form an xy yz pair. 2 comma 2, 3 comma 3 will form an xy yz pair. Now you need to have 2 comma 3, which is this. It is there. Again, you move check for all other elements like this. So you pick any x comma y comma z, any, or for all x comma y comma z pairs, you will have x comma z pair in R2. Therefore, R2 is transitive also. Therefore, R2 is equivalence. Okay. So R1 is just symmetric. R2 is equivalence. Now, what about R3?
It is reflexive, sir.
It is reflexive. Is it symmetric?
No, sir. We have 3 comma 1, but we don't have 1 comma 3.
Correct. Very good. So therefore, 3 comma 1 itself doesn't have the symmetric element, which is 1 comma 3. Therefore, straight away you can stop there at the first element itself and say this is not symmetric. Is this transitive?
No, sir.
So which pair breaks the
Uh,
property of transitivity?
we have 3 comma 1 and 1 comma 1, but no, we have 3 comma 1 and 1 second.
Okay. So anybody? Is R3 transitive?
Sir, it is transitive, sir.
It is transitive. So others?
Yes, sir, it is.
Okay.
It is, sir.
It is. Yeah, great. Maitreyi, Ramachandran, Jayashree, what do you guys think? Hemant? Okay. So it will be transitive. So you if you pick any pair or for every x comma y comma z, you will have x comma z in R3. Therefore, it will be transitive. It is reflexive, it is transitive, but it is not symmetric. Finally, what about R4?
It is not reflexive, sir.
It is not reflexive. Good. Is it symmetric?
No,
No,
sir.
sir.
Is it transitive?
Yes, sir.
Yes, sir.
Okay, I hear no and yes at the same time.
It is transitive, sir. 3 2 2 1 3 1.
Okay,
Sir,
so that
but
is not.
for 2 1, we don't have any element starting with 1.
That's fine. That's what we discussed so far. So if you have x comma y and you are not able to find y comma z pair, you leave it there and you conclude it is transitive for that particular element.
Okay, sir.
Okay. So yeah. So if you have only x comma y, there is no checking at all. You conclude that is transitive. If you have x comma y and y comma z, then check for x comma z. Okay. That's the only thing. So R1, you don't have 2 comma 2, it is not reflexive, it is not transitive. R2 is an equivalence relation. R3 is not symmetric. And finally, R4 is not symmetric, is not reflexive, but it is transitive. Okay. So I think uh, this is about relations. So the key takeaways are two things. The first thing is about transitivity. If you have only one element, x comma y, you straight away conclude that that particular relation is transitive. And if you have more elements also, and when you are looking at one element which has x comma y, but you are not finding a pair y comma z, then with respect to that element x comma y, that is transitive. There is no further checking at all. So you conclude With respect to that element that is transitive, and you move on to the next element. So the checking for transitivity, you start from first element to the last element. So you start from first element, treat it as xy, and see if you can find yz. If you can find yz, then check for whether there is xz or not. Depending on that, you decide transitivity with respect to that particular element. If it is transitive, then move on to the next element, treat that as xy, then search for yz pair. If you find yz, then go check for xz. If you are unable to find yz, then you just leave it as it is. You just conclude that that is transitive with respect to that element and move on to the next. Okay, so that is more important, and do not forget about this. So this is about relations. Now let's solve a couple of problems. Again, if you all interested to answer, if you don't want to put it in the chat or just unmute and tell, you can just go. Just a second. Okay, let me do test slides only. Let's ignore. We just had only 40 minutes. Have only 40 minutes to discuss. Okay, at least keep a pen and notebook ready. Just forget about this joinpt.com. Anyway, you joined with Gmeet, and keep a pen and notebook ready for solving the problems. Okay, so questions I will show you on the screen, and you can start solving it right away. You see the question, and then I will present the solution and we can have discussions. Okay, let's ignore this. Okay, we will start with this. So what you have to do is find the smallest natural number that leaves the remainder 2 and 3 when divided by 3 and 4 respectively. Okay, so when that particular natural number is divided by 3, it leaves a remainder 2, and when it divided by 4, it leaves a remainder 3. And there will be many natural numbers which satisfies this condition. What I want is the smallest natural number. Okay, so you can take some 3 minutes time, and hint is also provided to you. What you have to do is you have to create two different sets AB, where set A contains all the natural numbers that leaves the remainder 2 when divided by 3, and set B contains all the natural numbers that leaves the remainder 3 when divided by 4. And in order to satisfy both the conditions, you have to look into A union B or A intersection B. Which one? So you form two sets. If it has to satisfy both, it should be A intersection B, or you go look into A intersection B set or A union B set. So Jayashree says A intersection B. Okay. Any other answers?
Sir, 11.
Okay. So we got our first option as 11. So option A is 11. Let's see. Okay, you guys still have 2 more minutes. You can also put your answers in the chat.
Sir, 11, sir.
11. Okay.
Sir, it's 11.
11. So 3 people says it's 11. Okay. 4 says 11. Oh, okay. So yeah. So as you all say, it is 11. I think the answer will also be 11. But how do you solve this? So the answer is okay, but the solving will give you some intuition on when you see a similar kind of problem, this is how you should proceed. So when you create two sets A and B, you just have to create two sets which one set has all the natural numbers that leaves a remainder 2 when divided by 3, and other has a set which leaves remainder 3 when divided by 4. So if you create these sets, you will see in the set A, you will see 2, 5, 8, 11, 14, 17, 20, 23 and so on, right? And set B contains 3, 7, 11, 15, 19, 23, 27. Now, the next step is, what are we looking for? So we are looking for a natural number which satisfies both the conditions. So set A satisfies one condition, set B satisfies one condition. So both the conditions should be satisfied for our required natural number. So if both the conditions are required, then you need to go look for the elements which satisfies both, which are nothing but our natural number should be there in A as well as B. Therefore, you have to look in at A intersection B. If you look at A intersection B, you will find these elements 11, 23, 35 and so on. But among these elements, the smallest is 11. So the answer will be 11. Okay. Great. I hope this is clear for all. Is there anybody who have any doubt in this question? Okay. So let's move. So yeah, just quickly go through this things. So as you all know, complement of a set is basically all the elements that are not present in A. So if you have some elements in A, an A complement will simply be universal set minus all the elements that are present in A. And what is set subtraction? Set subtraction is kind of modifying your set. Okay, so you have a set A and you remove some elements from set A, and the resulting set is called A minus something. So if you have A and B as two sets and A minus B, so if you wanted to do a subtraction, what you do is you see the A intersection B part, so you just remove that part from A and the rest of the part is called A minus B. So it is simply the elements which contain only in A, not in B. Okay, so that is A minus B. Pictorially, this is what the yellow region is, what A minus B represents. Okay, and union and intersection, as you all know, union is basically include all the elements that are present in A as well as in B. So either A or B. And intersection is both A and B. So it should be there in both A and B, which is the common region between A and B. Okay, and there are a couple of set formulas which you can note it down. Many things you know, but I feel the third one will help you in some for solving some problems in our assignments. So the first one is well known to everybody, and of number of elements in A union B is simply number of elements in A plus number of elements in B minus number of elements in A and B. And number of elements in A minus B plus number of elements in A intersection B gives you number of elements in A. Similarly for B also. And the third one is the number of elements in A union B. You can write it as, the first formula is one way. The third one is another way. You can write it as number of elements in A minus B plus number of elements in A intersection B plus number of elements in B minus A. Okay. And final one is just the, if you have three sets, then n of A union B union C is written as n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of C intersection A plus n of A intersection B intersection C. Okay, so this is inclusion exclusion principle. Okay, so now let's solve some set theory problems also. Yeah, we still have 13 more minutes to go. We will quickly do this. So you have three sets and all the elements you see, each number you see, that is the cardinality of that particular region. So phi represents the region that is connected to all x, y, z intersection part. So there are 5 elements in it. So you treat it like that. Now find the cardinality of the set x minus z. So I repeat, all the elements you see, they are not region numbers, they are the cardinalities of that region. I hope everybody know what cardinality is. Cardinality is number of elements in that particular set.
Sir, 2.
Okay, x minus z is 2.
Sir, 5.
5. Okay, I3 also says it's 5. Okay, so the first thing I will just show you. So you just first identify the region which represents x minus z. So that will solve 90% of the problem. So if you see this particular region which is blue shaded is the region that represents x minus z. So after you see that particular region, then you just have to count the number of elements. So there is 1 which is contained only in x. There are 4 elements which are contained in x and y. Therefore, x minus z will contain 1 plus 4 elements, which is 5 elements. Okay. Okay. So the same sets x, y, z. Now what you have to do is find the cardinality of the set x union z intersected with y. So again, solve it in 2 steps. First, identify the region which represents x union z intersection y. Then count the elements present in that particular region.
Sir, 15.
Okay, I
Sir, 18.
15, 18. So yeah, I got 2 answers again. $15.
9, sir.
9. Okay. Okay. What do you guys think the region will be? So it's x union z intersected with y. Okay. You see the left top is x, right side top is y, and the bottom one is z. So first identify the region which represents x union z. Okay. So what is x union z? The left top and the bottom one. That you intersect it with y. So when you do the intersection, the common region will only be there. Common region which is x union z and vice. Okay. So first you represent the region which represents x union z. So x union z is this blue region. This blue region when intersected with y, what do you see? This blue region intersected with y, there will be 3 regions that are common among x union z and y, which are this 4, 5 and 6. Then if you count, you will get 15 as the cardinality. So the key thing is, see, the problem is very simple, looks simple. So I just gave you the cardinalities. I'm just playing around union intersection. Okay. But sometimes what happens is we might miss some region, we overlook it, and we may go wrong. Okay. So it's always better to solve problems in a stepwise method. Okay. So however small maybe the problem is, always start from basic ideas and then just build, use the formulas and everything that you know to get the answer. Okay, so we will end this particular session with this final question. So the next question I think I have already discussed with you. So these things I have discussed it with you. A and B lives in the same city. So let's discuss this third question and we can end the session here. Okay. So this third question is very similar to one of your graded assignment questions, maybe a variable change, I can say, or a number change, not even variables. Maybe the variables are also same. So you have a set S. Okay. This set S contains all the elements that are natural numbers, as well as it satisfies the condition that all the numbers should be less than or equal to 10. Now let R1 and R2 be relations from S to S defined as like this. So R1 is x comma y, all pairs x comma y such that y is equals to 2x. And R2, another relation R2, all pairs x comma y such that x comma y belongs to S and y is equals to x square. So the second in the pair, the second element is square of the first element in R2. And in R1, double of the first element. So the second element in the pair, the second element is double the first element. Now what I want is find the cardinality of the set R1 union R2 minus R2.
Sir, 4, sir.
Okay.
So 3, sir.
Okay, 3, 4. Okay, I'll give you a hint. Okay, this is for everybody. Just try solving this. So write down the set yes explicitly. So what all elements that will be present in the set yes? And again, remember, set yes starts from 0. Okay, because from the set of natural numbers starts from 0. Okay, write S explicitly, then write R1 and R2 explicitly. So write R1, what all elements that R1 can contain and R2 can contain. Then it will be easy. So then do R1 union R2, then remove R2 elements, and finally you will get a set. Just count how many elements are present in that particular set. That will give you the cardinality. Okay. So we have 4 more minutes left. So 2 minutes I will give you to solve, and the last 2 minutes we will discuss the solution. If people have solved it, then I have a question for you. You can solve. So this is an extra question who have solved this particular question.
Sir, I'm getting 2, sir.
Okay, let's see. We will see. Okay, so you see one question boxed in a white box. Suppose you have a function defined from set of natural numbers to set of natural numbers, and is defined as f of x is equals to ax. Okay, a is not known, and it is said that a is a biject. See, f is a bijective function. Now you have to find the value of a. Okay, I suggest just note this down so that I will move to the previous question. So f of x is equals to ax is a bijective function. Find the value of a. So people who have solved this, try solving that. But people who are solving, we have only 1 more minute left. Okay, so I think time is up. Let's discuss the solution because I don't want to take extra time from you guys. Okay, so let's start. Write down R1 and R2 explicitly. When you write down, you see R1. Can I write all these things? 0, comma 0. Will 0, comma 0 be in R1?
Yes, sir.
1, comma 2,
Yes, sir.
2, comma 4, 3, comma 6, 5, comma 10, 6, comma 12.
Sir, but that will be greater than 10.
Right. So 6, comma 12 will not be an element. Therefore, R1 contains only these 6 elements, not more than that. These are the only 6 elements that R1 can contain. Similarly, if you write down R2, 0, comma 0, 1, comma 1, 2, comma 4, 3, comma 9. There will not be any 4, comma 16. Okay. So you have R1 and R2 now. You just have to find R1 union R2 first. So what will be R1 and R1 union R2? 0, comma 0, 1, comma 1, 1, comma 2, 2, comma 4, 3, comma 6, 3, comma 9, 4, comma 8, 5, comma 10. That's it. Now, once you have R1 union R2, what you have to do? You have to subtract the R2 elements from R1 union R2. The third step. So, identify the R2 elements which are in R1 union R2. So, you will see 0, comma 0, 1, comma 1, 2, comma 4, 3, comma 9 which are there in R2. You remove them and the resulting set will be 1, comma 2, 3, comma 6, 4, comma 8, 5, comma 10. Hence, the cardinality will be 4. Okay. So I think people would have missed one element in between. So what is that element you missed? Those who got 3 or 2.
I missed 2, comma 4, sir.
Okay. But there is no 2, comma 4 here. But anyway, what do you missed as 2, comma 4?
Like while taking it, like I didn't consider all of them, sir. I made a mistake.
Okay. Okay, fine. Now you understood, right? So those who got wrong, I think this explanation gives you much clarity.
Sir,
Okay. So yeah, we clicked 7. So I will stop here. The people who have solved the extra question, have anybody solved it? No? Okay. Okay, then I think everybody take this as an exercise and you can post it in our Google groups. So take this question and try solving this. I just need the value of A. If you got the value of A, just use the forum. Just write down the question there and you can give your answers and start a discussion. Then the others will also join and participate in the discussion. Even I
Sir,
will give my inputs there. Yeah.
sir, here A should be equal to X, no, sir?
If A is equals to X, then it will become f of X is equals to X square, right?
Yes, sir.
So
Then,
do you think X square is a bijective function? Set of natural numbers to set of natural numbers. In order to be bijective, the codomain should be the range.
yes, sir, here the domain and range are both the same. So, and since the domain is the codomain, so X square can be an answer, no, sir?
I don't think. See, for bijectiveness, you need to have subjectivity also should be satisfied, right? Will there be any mapping to the number 8? So
So
8
for
is in
A,
your codomain, right?
yes, sir.
But will there be any element that maps to 8?
8 will match to itself, no, sir? X square.
No, no, no. If 8 matches to 8, then that function will not be x square, right? See, if you say function is equals to x square, what does it imply? If you input 8, your output will be 64. If you input 2, your output will be 4. Anyway, you just start a discussion in our Google groups. We can discuss there also. Okay.
Okay, sir.
Okay. So try thinking about this problem, and if you got the answer, please post it in discussion forums and we will discuss there. So even I will participate in the discussion.